Welcome to Nap Labs, where we explore the universe at the pace of a dream. Tonight, we turn our gaze toward a world that once breathed, a planet that held oceans beneath open skies, a place where rivers carved through ancient stone under a thicker atmosphere than it knows today. Mars is not just a neighbor in the dark. It is a mirror held up to Earth, showing us what a world looks like when its heartbeat fades, when its magnetic shield collapses, when its warmth bleeds away into the cold vacuum of space. This is the story of a dying world, told slowly, softly, as you rest. And if you'd like, drop a comment below with where you are in the world right now, what time it is as you listen. It connects us all under the same stars. Close your eyes if you wish. Let the weight of the day dissolve. We are going to travel 4.5 billion years backward and 55 million kilometers outward to a rusty sphere that glows faintly in our night sky, a world that whispers of what was and what could have been. Mars hangs in the darkness like an ember cooling in the hearth of the solar system. It is smaller than Earth, just over half our diameter, with a mass only 11% of ours. If Earth were a billiard ball, Mars would be a marble rolling beside it. Yet this modest world has captivated humanity for millennia. The ancient Egyptians called it Horus of the horizon. The Greeks named it Ares. The Romans gave it the name we use now, after their god of war, inspired by its blood-red color in the night sky. That color comes from iron oxide, rust, covering its surface like the patina on an old blade left out in the rain. But Mars was not always a desert. The story we are about to unfold is one of transformation, of loss, of a planet that once held promise and now holds only memory. Let us begin not with what Mars is, but with what it was. 4.5 billion years ago, the solar system was a disk of dust and gas swirling around a young sun. Particles collided, stuck together, grew. Planetesimals formed, then protoplanets, and finally, the worlds we know today. Mars coalesced in the outer region of the inner solar system, beyond Earth's orbit, where the protoplanetary disk was thinner and colder. This is why Mars never grew as large as Earth or Venus. There was simply less material to gather in its orbital path. In those early days, Mars was a violent place. Asteroids and comets pummeled its surface, delivering water, organic molecules, and kinetic energy. The planet was molten, its interior churning with heat from radioactive decay and the energy of countless impacts. A magnetic field formed, generated by a dynamo deep in its liquid iron core. This magnetic shield wrapped around the young planet like an invisible cocoon, deflecting the solar wind, protecting the atmosphere from being stripped away particle by particle. And there was an atmosphere, thick, warm, rich with carbon dioxide and water vapor. Volcanic eruptions sent plumes of gas into the sky. The surface cooled, rain fell, rivers flowed. This was the Noachian period, named after Noach's Terror, one of the oldest terrains on Mars, a time that lasted from roughly 4.1 billion years ago to 3.7 billion years ago. During this epoch, Mars may have been more Earth-like than at any other time in its history. Imagine standing on the shore of a Martian sea during the Noachian. The sky above you is not the butterscotch yellow we see in images from rovers today, but perhaps a deeper orange, or even a pale blue near the zenith, where the atmosphere is thickest. Water laps at your feet, cold but liquid, kept from freezing by a greenhouse effect, strong enough to hold the surface temperature above 0 degrees Celsius in some regions. Mountains rise in the distance, their peaks dusted with frost. Clouds drift overhead, not the thin wisps of carbon dioxide ice we see now, but thick water clouds that bring rain in the afternoons. This is not fantasy. This is the Mars that geological evidence suggests once existed. Valley networks snake across the ancient highlands, carved by flowing water. Deltas spread out where rivers once emptied into lakes. Minerals that form only in the presence of liquid water, clays and sulfates, are embedded in rocks that rovers have ground into and analyzed. Curiosity, the rover that has been exploring Gale Crater since 2012, found rounded pebbles that could only have been shaped by a stream, evidence of water flowing at a depth of perhaps a meter, moving at nearly a meter per second. But this watery world was not destined to last. Something went wrong inside Mars. The planet is small, and small worlds cool faster than large ones. The ratio of surface area to volume favors heat loss. Earth, being more massive, retains its internal heat, keeping its outer core molten, maintaining the convective currents that generate our magnetic field. Mars, with only about half Earth's radius, could not hold on to its warmth as long. Its core began to cool and solidify. Between 4.1 and 4 billion years ago, the Martian dynamo failed. The magnetic field collapsed. This was not a sudden event, not a switch flipping off, but a gradual weakening over millions of years, a fading shield that could no longer hold back the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at speeds of 300 to 800 kilometers per second. When this wind encounters a magnetosphere, it is deflected around the planet, like water parting around a stone in a stream. But when the magnetosphere disappears, the solar wind strikes the atmosphere directly. It ionizes the upper layers, stripping atoms and molecules away into space. On Earth, this loss is negligible because our magnetic field remains strong. On Mars, it became catastrophic. Over hundreds of millions of years, the atmosphere thinned. The greenhouse effect weakened. Temperatures dropped. Water that once flowed on the surface began to freeze, to evaporate, to be lost to space. The planet was bleeding into the void, and there was nothing to stop it. NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, arrived at Mars in 2014 with the specific goal of understanding this atmospheric loss. Its instruments measured the rate at which ions are still being stripped from the Martian atmosphere today. The numbers are startling. Mars is losing roughly 100 grams of atmosphere every second. That might not sound like much. 100 grams, the weight of a small apple, escaping into space every second. But multiply that by billions of years, and you begin to understand the scale of the loss. The atmosphere that once pressed down on the surface with perhaps the equivalent of Earth's sea level pressure, 600 to 700 millibars, has dwindled to just 6 millibars today, less than 1% of Earth's atmospheric density. At such low pressure, liquid water cannot exist on the surface. It either freezes or sublimates directly into vapor. The triple point of water, the temperature and pressure at which liquid, solid, and gas can coexist, is 6.1 millibars and 0.01 degrees Celsius. Most of Mars today sits right at or below that threshold. Water ice exists in abundance, locked in the polar caps, buried in the soil, frozen in the regolith. But rivers and lakes and seas are ghosts now, features preserved only in the stone. As the atmosphere thinned, as the water disappeared, Mars entered the Hesperian period roughly 3.7 to 3 billion years ago. Volcanic activity continued. Lava flows spread across the surface. Great flood channels were carved, possibly by sudden releases of water from underground aquifers, catastrophic outbursts that briefly brought liquid water back to the surface before it froze or evaporated. But the overall trend was toward desiccation, toward cold, toward silence. And yet, even as the planet dried, life might have clung on beneath the surface, in pockets where geothermal heat still warmed the rock, where water remained liquid in the dark. This is speculation, but it is grounded in what we know about life on Earth, where microbes thrive kilometers below the surface, in hot springs, in ice, in every niche where water and energy can be found. Let us drift forward now, across billions of years, to the Mars we observe today. It is a world of dust and stone, of craters and canyons, of towering volcanoes and vast plains. The surface temperature averages minus 63 degrees Celsius, though it can rise above freezing near the equator on a summer afternoon and plunge to minus 125 degrees Celsius at the poles in winter. The atmosphere, thin as it is, still produces weather. Dust devils spiral across the plains. Dust storms grow and occasionally engulf the entire planet, shrouding it in a haze that can last for months. Mars rotates once every 24 hours, 37 minutes, and 22 seconds, remarkably close to Earth's day. This near match has always felt like a kindness, a familiarity in a place so alien. The planet's axis is tilted at 25.2 degrees, again similar to Earth's 23.5 degrees, giving Mars distinct seasons as it orbits the Sun once every 687 Earth days. But Mars's orbit is more elliptical than Earth's. At perihelion, its closest approach to the Sun, Mars is 206.7 million kilometers away. At aphelion, it swings out to 249.2 million kilometers. This difference, 42.5 million kilometers, is significant. It means that southern hemisphere summers occur when Mars is closest to the Sun, making them shorter but more intense than northern summers. The southern polar cap shrinks dramatically during summer, sublimating carbon dioxide ice directly into gas, thickening the atmosphere temporarily before it refreezes in winter. The northern cap is different. It is larger and mostly water ice, with a thin seasonal layer of carbon dioxide frost on top. If you could melt all the water ice in the northern polar cap, it would cover the planet to a depth of about 22 meters. Not enough to restore the ancient oceans, but a reminder of the water that once was. Standing on the surface today, you would see a landscape both beautiful and barren. The sky lit by a sun that appears about 2/3 the size it does from Earth, glows with that characteristic salmon hue during the day, a result of dust particles scattering the sunlight. At sunset, something magical happens. The sky near the sun turns blue, a reversal of Earth's red sunsets, because the dust scatters the red light away, allowing the shorter blue wavelengths to shine through. The ground beneath your feet is regolith, not soil, because soil implies the presence of organic matter from decayed life. This is rock, ground down by eons of meteorite impacts, oxidized by trace amounts of oxygen in the thin air, turned into a fine powder that clings to everything. Rocks jut out at odd angles, fractured by the freeze-thaw cycles of ancient water ice, cratered by small meteorites that made it through the thin atmosphere without burning up completely. The gravity is 38% of Earth's, a gentle tug that would make walking feel like bounding, each step carrying you farther than you intended. The silence is profound. There is no wind strong enough to carry sound well through the thin air. A dust devil might pass nearby, and you would see it, but barely hear it. A boulder tumbling down a slope would make a muted thud, swallowed by the emptiness. The geography of Mars tells the story of its death in a language written in stone. The planet is divided into two distinct hemispheres. The southern hemisphere is ancient, cratered, high-standing terrain dating back to the Noachian. The northern hemisphere is younger, smoother, lower by an average of 5.5 kilometers. This dichotomy is one of the great mysteries of Mars. Why are the two halves so different? One hypothesis suggests a massive impact early in Martian history, a collision with an object perhaps 1/6 the diameter of Mars itself, excavating the northern lowlands and leaving the southern highlands untouched. Another idea invokes mantle convection patterns that drove crustal thinning in the north. The truth may be a combination of factors or something else entirely. Mars keeps its secrets close. Then there is Valles Marineris, the grandest canyon in the solar system. Stretching more than 4,000 kilometers along the Martian equator, it is nearly as long as the width of the United States. At its deepest, it plunges 7 kilometers below the surrounding plains. For comparison, Earth's Grand Canyon is 446 kilometers long and reaches depths of just under 2 kilometers. Valles Marineris is not a canyon carved by water, but a tectonic feature, a series of collapsed rift valleys formed as the Tharsis Bulge rose to the west, stretching and cracking the crust. The Tharsis Bulge itself is a volcanic province, a massive uplifted region crowned by 3 enormous shield volcanoes, Arsia Mons, Pavonis Mons, and Ascraeus Mons. To the northwest stands Olympus Mons, the largest volcano in the solar system, rising 21.9 kilometers above the surrounding plains, with a base that spans 620 kilometers. If you stood at its base and looked up, the summit would be beyond the horizon, hidden by the curve of the planet. If you stood at the summit and looked down, the ground below would be lost in haze. Olympus Mons is a shield volcano, built by countless eruptions of low-viscosity lava that spread out in thin layers, piling up over millions of years. It is so large because Mars lacks plate tectonics. On Earth, a volcanic hotspot like the one that created the Hawaiian Islands eventually moves as the tectonic plate drifts overhead, creating a chain of islands. On Mars, the crust remains stationary, allowing the hotspot to keep feeding the same volcano, building it higher and higher until the magma supply runs out. These volcanoes were active relatively recently in geological terms. Lava flows on Olympus Mons may be as young as 2 million years old. Mars is not geologically dead, only sleeping, its internal fires banked but not extinguished. Water, or the memory of it, haunts Mars. Everywhere we look, we see evidence of its presence in the past. The valley networks in the southern highlands, mentioned earlier, are the most obvious signs. They branch like the veins of a leaf, tributaries joining into larger channels, carved by persistent flow over long periods. These are not the catastrophic flood channels like those that gouged out the Kreis-Planitia region, where water burst forth in unimaginable volumes, scouring the landscape in days or weeks. The valley networks suggest a stable hydrological cycle, rain or snowmelt feeding streams that flowed for thousands or millions of years. Gale Crater, where Curiosity roams, was once a lake. Sediment layers within the crater, exposed in the slopes of Mount Sharp, the central peak, show a history of wet and dry periods. The rover has drilled into mudstones that formed at the bottom of a lakebed, minerals deposited in still water. It has found organic molecules, complex carbon compounds that could be the remnants of ancient life or simply the products of non-biological chemistry. We do not know yet. The distinction is tantalizing. Jezero Crater, where the Perseverance rover landed in February 2021, is another ancient lake. A river once flowed into it from the west, carrying sediment and depositing it in a delta. Perseverance is collecting samples from this delta, drilling into rocks and sealing cores into tubes that a future mission will retrieve and bring back to Earth. Those samples might contain signs of past life, biosignatures locked in stone for billions of years. Or they might not. The search continues. And then there's the question of liquid water today. The surface conditions do not allow it, as we have discussed. But beneath the surface, possibilities linger. In 2018, radar data from the Mars Express orbiter suggested the presence of a subsurface lake of liquid water beneath the southern polar cap, buried under 1.5 kilometers of ice. The radar reflections showed a bright spot consistent with liquid water, kept from freezing by the pressure of the ice above, and perhaps by dissolved salts that lower the freezing point. Subsequent analysis has been debated. Some scientists are convinced. Others think the signal could be explained by clays or saline ice. The data is ambiguous, the interpretation uncertain. Mars, once again, does not give up its secrets easily. But whether or not liquid water exists beneath the poles, we know it is there in frozen form, vast quantities of it. Ground-penetrating radar from orbit has revealed ice just centimeters below the surface in many regions. The Phoenix lander, which touched down near the North Pole in 2008, dug into the soil and exposed bright white ice. Cameras watched as some of that ice sublimated over the course of several days, disappearing into the thin air. If we wanted to, if we sent humans to Mars, we could extract water from the regolith. Heating the soil would release the ice as vapor, which could be condensed and purified. This is not science fiction. This is engineering. Difficult but doable. Water for drinking, for growing food, for producing oxygen and hydrogen as rocket fuel. Mars hoards its water, but it is there for those patient and clever enough to claim it. The moons of Mars are small, dark, and strange. Phobos and Deimos, fear and dread, named after the sons of Ares in Greek mythology. They were discovered in 1877 by Asaph Hall at the United States Naval Observatory, though their existence had been speculated about for centuries. Jonathan Swift, in his 1726 novel Gulliver's Travels, described 2 Martian moons, a fictional detail that turned out to be true. How did Swift guess correctly? Pure coincidence, or perhaps an understanding that if Earth had one moon and the outer planets had many, Mars, sitting between them, might reasonably have a couple. Phobos is the larger of the 2, an irregular lump of rock measuring about 27 kilometers across at its widest. It orbits just 6,000 kilometers above the Martian surface, closer to its planet than any other moon in the solar system orbits its primary. From the surface of Mars, Phobos would appear about 1/3 the size of our moon in Earth's sky, but it would zip across the sky in just over 4 hours, rising in the west and setting in the east, moving faster than Mars rotates. It would show phases, waxing and waning as it orbited. Phobos is doomed. Tidal forces are slowly pulling it closer to Mars, lowering its orbit by about 2 meters every century. In 50 to 100 million years, it will either crash into the surface or, more likely, be torn apart by tidal forces as it crosses the Roche limit, the distance at which the planet's gravity overcomes the moon's own cohesion. When that happens, Mars will have a ring, a temporary feature made of debris from its shattered moon, glittering in the sunlight for a few million years before the particles spiral down and pepper the surface. Deimos is smaller, about 15 kilometers across, and orbits farther out, 20,000 kilometers above the surface. It is more sedate, taking 30 hours to complete one orbit. From Mars, it would look like a bright star moving slowly across the sky, never showing phases visible to the naked eye. Both moons are dark, reflecting only about 6% of the sunlight that hits them, similar to charcoal. They are likely captured asteroids, immigrants from the asteroid belt that wandered too close to Mars and were snared by its gravity. Their composition, rich in carbonaceous material, supports this origin story, though some scientists argue they could be debris from a giant impact on Mars itself, blown into orbit and coalescing into these two misshapen bodies. Standing on Phobos would be surreal. The gravity is so weak, about 1/1000th of Earth's, that you could jump and reach escape velocity if you pushed hard enough. You would drift off into space, becoming your own tiny moon orbiting Mars. The surface is heavily cratered, the largest being Stickney crater, 10 kilometers across, nearly half the width of Phobos itself. The impact that created Stickney almost shattered the moon completely. Grooves radiate across the surface, possibly fractures from that impact or features created by rolling boulders dislodged by other impacts. Mars hangs in the sky above you, enormous, filling a quarter of your field of view. You would see it rotate, watching weather patterns shift. Dust storms bloom and fade. The polar caps wax and wane with the seasons. You would be the closest observer to the Martian surface without actually standing on it, a lonely outpost in the dark. The human relationship with Mars stretches back to the earliest stargazers. Its reddish hue made it stand out among the stars, and its wandering motion across the sky, moving forward then backward in retrograde loops, marked it as something different, a planet, a wanderer, from the Greek word planets, meaning wanderer. In the late 1800s, as telescopes improved, Mars became a subject of intense scrutiny. Giovanni Schiaparelli, an Italian astronomer, observed Mars during its close approach to Earth in 1877 and mapped features he called canali, an Italian word meaning channels. The term was mistranslated into English as canals, implying artificial construction. This misunderstanding sparked a wave of speculation. If there were canals on Mars, they must have been built by an intelligent civilization, a Martian race engineering their world to bring water from the poles to the arid equatorial regions. Percival Lowell, an American astronomer, became the most vocal proponent of this idea. He built an observatory in Flagstaff, Arizona, and spent years observing and drawing Mars, mapping an intricate network of canals he believed were proof of Martian engineers at work. His books and lectures captivated the public. Mars was not just a planet. It was a world inhabited by beings struggling against a dying environment, desperately trying to sustain their civilization as their planet dried up beneath them. It was a beautiful, tragic narrative. It was also wrong. As telescopes improved and photographic techniques advanced, the canals vanished. They had never existed except as optical illusions, the human brain's tendency to connect random features into patterns. The Martian engineers were projections of our own hopes and fears, not inhabitants of the red planet. But the fascination remained. In 1898, H.G. Wells published The War of the Worlds, imagining Martians invading Earth in desperate search of a new home. In 1950, Ray Bradbury gave us The Martian Chronicles, a poetic exploration of human colonization and the ghosts of a Martian civilization. Mars became a canvas for our dreams and nightmares, a place to explore themes of exploration, imperialism, survival, and loss. The space age brought truth to replace speculation. The first successful mission to Mars was Mariner 4, a NASA flyby probe that reached the planet in July 1965. It returned 22 images, grainy black and white photographs showing a cratered, moon-like surface. The public was disappointed. This was not the Mars of Lowell or Bradbury. This was a dead world, cold and cratered, with no sign of canals or cities or life. But Mariner 4 had only glimpsed a small portion of Mars, and it happened to fly over some of the oldest, most heavily cratered terrain. Subsequent missions revealed more complexity. Mariner 9, which arrived in 1971, was the first spacecraft to orbit another planet. It mapped the entire surface and discovered the giant volcanoes, the vast canyon of Valles Marineris, and clear evidence of ancient water flow. Mars was not a dead twin of the Moon. It was a world with a history, a story written in lava and water and wind. The Viking program in 1976 sent 2 landers to the surface. They tested the soil for signs of life, running experiments designed to detect microbial metabolism. The results were ambiguous, frustrating, tantalizing. Some experiments gave positive results that could indicate biological activity, but could also be explained by unusual chemistry in the Martian soil. The scientific consensus leaned toward non-biological explanations, but the debate has never fully closed. Decades passed. Missions succeeded and failed. Mars Observer was lost in 1993, just before entering orbit. Mars Polar Lander crashed in 1999. The Mars Climate Orbiter was destroyed the same year due to a navigation error caused by a mix-up between metric and imperial units. A reminder that Mars does not forgive mistakes, but successes accumulated. Mars Global Surveyor mapped the planet in exquisite detail from 1997 to 2006. Mars Odyssey, arriving in 2001, discovered vast amounts of subsurface ice. Mars Express, a European mission launched in 2003, carried ground-penetrating radar and found those controversial bright spots beneath the polar cap. On the surface, rovers explored. Sojourner, a tiny rover about the size of a microwave oven, rolled off the Mars Pathfinder lander in 1997 and spent 83 days exploring a small patch of Ares Vallis. Spirit and Opportunity, twin rovers launched in 2003, were designed to last 90 days. Spirit operated for over 6 years. Opportunity, the rover that wouldn't die, kept going for 14 years, traveling over 45 kilometers until a global dust storm in 2018 blocked out the sun and drained its batteries beyond recovery. Curiosity, the size of a car, landed in Gale Crater in August 2012. It is still operating, still climbing Mount Sharp, still drilling into rocks and analyzing their composition. Perseverance joined it in February 2021 in Jezero Crater, equipped with a small helicopter named Ingenuity that proved powered flight is possible in the thin Martian air. Each mission adds pieces to the puzzle. Each discovery raises new questions. Mars is no longer a mystery waiting to be solved, but a complex story being slowly read, page by page, year by year. Why does Mars matter? Why do we keep sending robots to crawl across its dusty plains, to drill into its rocks, to stare at its sky? The answer lies partly in science, partly in curiosity, and partly in survival. Scientifically, Mars is a laboratory for understanding planetary evolution. It is similar enough to Earth to make comparisons meaningful, different enough to illuminate what makes a planet habitable. Mars had water, an atmosphere, possibly life. Earth has water, an atmosphere, and definitely life. What made the difference? Why did one planet thrive while the other withered? The answer seems to be size. Size determined how long the interior stayed hot, which determined how long the magnetic field lasted, which determined how much atmosphere could be retained, which determined whether liquid water could persist on the surface. It is a cascade of consequences stemming from that initial condition. Mass. Mars was born too small, and that sealed its fate. But there is more to the story. Venus is almost Earth's twin in size, yet its surface is a hellscape, 470 degrees Celsius, hot enough to melt lead, with an atmosphere 90 times denser than Earth's, crushing and corrosive. Size is not the only factor. Distance from the sun matters. Composition matters. Chance events, like the giant impact that formed our moon, which may have played a role in stabilizing Earth's climate, matter. Planetary evolution is not deterministic. It is chaotic, contingent, shaped by a million variables interacting over billions of years. Understanding Mars helps us understand Earth. It teaches us how fragile habitability can be, how easily a world can tip from life-supporting to lifeless. And that knowledge is not academic. Earth's climate is changing. Human activity is altering the composition of our atmosphere, warming the planet, melting ice caps, shifting weather patterns. Mars is a warning, a preview of what can happen when an atmosphere is lost, when water disappears, when a planet cools and dies. We cannot let Earth become Mars, but Mars is also a beacon. It is the most accessible, potentially habitable world beyond Earth. It has water, carbon dioxide, minerals, sunlight. It has a day length similar to Earth's, seasons, a surface you can stand on. It is harsh, yes. The air is unbreathable. The radiation is deadly. The cold is extreme. But these are engineering problems, not fundamental barriers. Humans are clever. We build habitats, generate power, recycle air and water, grow food in greenhouses. We have survived Antarctica, the deep ocean, the vacuum of low Earth orbit, we can survive Mars. There is talk of sending humans to Mars in the coming decades. NASA's Artemis program aims to return humans to the Moon as a stepping stone. SpaceX is developing the Starship system with Mars colonization explicitly in mind. The challenges are enormous. The 6 to 9 month journey, the cosmic radiation exposure, the psychological toll of isolation, the difficulty of landing heavy payloads on Mars's thin atmosphere, the need for in situ resource utilization to produce fuel and oxygen for the return trip. But these challenges are being addressed piece by piece. Why go? Some say for the adventure, the spirit of exploration that drove humans to cross oceans and climb mountains. Some say for the science, the discoveries that can only be made by humans on the ground, with their intuition and adaptability. Some say for the survival of the species, to become a multi-planetary civilization, to ensure that no single catastrophe can wipe us out. All of these reasons are valid. All of them together create a compelling case. Imagine the first human footsteps on Mars. The lander has touched down in a carefully chosen location, perhaps near the equator where temperatures are milder, or near the polar regions where water ice is accessible. The crew has waited inside for dust to settle, for systems to be checked, for the moment to arrive. The hatch opens. An astronaut in a bulky suit climbs down the ladder. Their boot touches the regolith, leaving a print that will remain undisturbed for millions of years until wind or impact erases it. They look around. The sky is that familiar salmon pink. The sun is smaller, paler, casting long shadows. The horizon is closer than on Earth, just 3.2 kilometers away compared to 4.7 kilometers on Earth. Because Mars is smaller, its curvature tighter. Mountains rise in the distance. Rocks lie scattered across the ground, some half buried, some perched precariously. There is no sound but their own breathing, their heartbeat, the hum of the life support systems. They speak. The words are transmitted back to Earth, taking anywhere from 4 to 24 minutes to arrive, depending on where the planets are in their orbits. Earth receives the message, and the world erupts in celebration. Humanity has taken its first step toward becoming a two-world species. The first mission will be short, perhaps 30 days on the surface, just long enough to deploy equipment, conduct experiments, collect samples, and prove it can be done. Subsequent missions will stay longer, build more infrastructure, establish a permanent presence. Habitats will be constructed using Martian soil for radiation shielding, 3D printing structures from regolith mixed with polymers. Solar panels and nuclear reactors will provide power. Greenhouses will grow food, not just for nutrition, but for morale, for the psychological comfort of seeing green leaves, smelling soil, tasting fresh vegetables. Water will be extracted from the ground, purified, split into hydrogen and oxygen. The oxygen will be breathed. The hydrogen combined with carbon dioxide from the atmosphere to produce methane fuel. Rovers and drones will explore farther and farther from the base, searching for resources, for sites of scientific interest, for signs of past life, and perhaps, eventually, for signs of present life. Because despite the harshness of the surface, despite the thin air and the radiation and the cold, life might still exist on Mars. Not on the surface, but beneath it, in aquifers warmed by geothermal heat, in pockets of brine that resist freezing, in the deep subsurface where conditions may not have changed as dramatically as they did at the surface. Finding life on Mars, even if it is just microbes, even if it is extinct and preserved only as fossils, would be one of the most profound discoveries in human history. It would tell us that life is not unique to Earth, that it arises wherever conditions allow, that the universe may be teeming with biology. It would raise immediate questions. Did Martian life arise independently from Earth life, or did it share a common origin, seeded by meteorites carrying microbes between the two planets? How similar is it to Earth life? Does it use DNA, the same genetic code, the same chemistry, or did it evolve something entirely different? And if we find no life, that would also be significant. It would tell us that even on a world with water, with carbon, with energy, life did not take hold or did not survive. It would suggest that life is rare, that Earth is precious, that we should take care of the one world we know supports it. Mars's future is as uncertain as its past. The sun is slowly brightening, increasing in luminosity by about 10% every billion years. In a billion years, Earth's oceans will begin to evaporate. The runaway greenhouse effect will take hold, and our world will become uninhabitable. Mars, farther from the sun, will warm. Its surface temperature will rise. The polar caps will melt, releasing carbon dioxide and water vapor into the atmosphere, thickening it, strengthening the greenhouse effect. For a brief window, geologically speaking, Mars might become habitable again. But this is far in the future, so distant that it is almost meaningless to us now. What matters is the present, the next few decades, the next few centuries. What we do with Mars, how we explore it, whether we settle it, whether we find life or introduce life, will shape our understanding of our place in the cosmos. There is a philosophical question embedded in all this. If we send humans to Mars, if we build cities there, if we terraform the planet, warming it, thickening the atmosphere, melting the ice, are we restoring Mars to what it once was, or are we imposing our will on a world that has its own integrity, its own right to remain as it is? Some argue that Mars is already dead, that there is no harm in making it livable for us. Others counter that we should tread carefully, that we do not yet understand Mars well enough to alter it responsibly, that any indigenous life, if it exists, has a claim that supersedes our convenience. These are not easy questions. They will be debated for generations, but they are worth asking now, before we commit to irreversible actions, before we repeat on another world the mistakes we have made on our own. Let us return to the surface of Mars as it is today, not as it was or might be, but as it exists in this moment. The rovers continue their slow exploration. Perseverance has cached several sample tubes now, sealed containers holding pieces of Martian rock and regolith, placed carefully on the ground in a depot where a future mission can retrieve them. The plan is ambitious. A fetch rover will collect the tubes, transfer them to a small rocket, which will launch from the Martian surface, the first rocket ever to launch from another planet. That sample container will be captured by an orbiter, brought back to Earth, and delivered to laboratories where scientists can analyze the material with instruments too large and complex to send to Mars. Those samples might contain answers. They might hold organic molecules, isotopic signatures, mineral formations that can only be explained by biology, or they might not. But even negative results are informative. Knowing what Mars is not helps us understand what it is. Ingenuity, the little helicopter, defied all expectations. It was meant to fly 5 times, a technology demonstration to prove that powered flight is possible in air 1% as dense as Earth's. It has flown more than 70 times, covering distances, scouting terrain, showing that aerial exploration of Mars is not just possible, but practical. Future missions will carry larger helicopters or fixed-wing aircraft able to cover vast distances, to peer into craters and canyons, to go where rovers cannot. The orbiters circling above continue their watch. Mars Reconnaissance Orbiter, with its high-resolution camera, has imaged the entire planet in stunning detail, revealing features as small as a dining room table. It has watched seasonal changes, tracked dust storms, monitored the polar caps. MAVEN continues measuring atmospheric loss, building a picture of how Mars's atmosphere escapes into space. The European Space Agency's Trace Gas Orbiter analyzes the thin air, searching for methane, a gas that could indicate either geological activity or biological processes. Methane detections on Mars have been controversial, sometimes present, sometimes absent, never conclusively explained. The mystery endures, and new missions are planned. China landed its Zhurong rover in May 2021, joining the international community in exploring Mars. The United Arab Emirates Hope orbiter, arriving in February 2021, studies the Martian atmosphere and weather patterns. Japan, India, and the European Space Agency are planning future missions. Mars is becoming a destination, not just for superpowers, but for any nation with the ambition and resources to reach it. This is good. The more eyes on Mars, the more instruments studying it, the faster we will learn. Science thrives on collaboration, on multiple perspectives, on the cross-checking of results. Mars is too large, too complex, for any single nation or agency to understand alone. There is a particular crater on Mars that holds a special place in the imagination of astrobiologists. Gusev crater is a shallow depression, roughly 160 kilometers across, with what appears to be a channel, Ma'adim Vallis, leading into it from the south. The hypothesis was that this channel once carried water, filling Gusev with a lake. The Spirit rover was sent there in 2004 to test this hypothesis, to look for lakebed sediments, for shorelines, for evidence of standing water. What Spirit found was volcanic rock, basalt, layer upon layer, from lava flows that had filled the crater floor, burying any ancient lake deposits beneath meters of solidified magma. It was disappointing at first, but Spirit pressed on, climbing into the Columbia Hills at the edge of the crater, and there, in the rocks of the hills, it found what it had been sent to find: minerals that form in water, sulfates and iron oxides, evidence that water had once been present, altering the rocks, leaving its signature. Spirit's journey became an epic. It climbed hills, descended into craters, survived Martian winters by parking on sun-facing slopes to keep its solar panels illuminated. It drove with one wheel jammed, dragging it behind like a wounded leg, leaving a furrow in the soil. In 2009, it became stuck in a patch of soft regolith, wheels spinning, unable to gain traction. Engineers on Earth spent months trying to free it, commanding it to rock back and forth to try different combinations of wheel movements. Nothing worked. Spirit was trapped. NASA declared the mission over as a mobile explorer, but continued using Spirit as a stationary science platform. It measured the Martian wind, the composition of the soil, the dust settling on its panels. Its last communication was received in March 2010. The Martian winter was approaching. Spirit's power levels dropped. It fell silent. Attempts to re-establish contact continued for a year, but the rover never woke up. It sits there still, in the Columbia Hills, a monument to human curiosity, to the drive to explore, to the machines we send forth as extensions of ourselves. Opportunity's story is equally moving. It landed on the other side of Mars, in Meridiani Planum, a flat plain rich in the mineral hematite, which often forms in water. Opportunity found evidence of past water almost immediately. Tiny spherules of hematite, nicknamed blueberries, formed in acidic water that percolated through the rock. It studied outcrops that showed crossbedding, layers of sediment laid down by flowing water or wind. It found veins of gypsum, a sulfate mineral that precipitates from water. Opportunity kept going. 90 days stretched into months, then years. It drove to Victoria Crater, peered over the edge, descended into it, explored its walls, climbed back out. It drove 21 kilometers to Endeavour Crater, a much larger and older impact structure, and spent years exploring its rim, finding clay, minerals that form in water with a neutral pH, more hospitable to life than the acidic conditions recorded in the rocks near its landing site. In June 2018, a dust storm began. It grew rapidly, engulfing the planet. The sky above Opportunity darkened. Its solar panels, already dusty, received almost no sunlight. Power dropped. The rover sent a final transmission and went into low power mode to wait out the storm. The storm lasted months. When it cleared, Opportunity did not respond. Engineers sent commands, listening for any signal. Silence. In February 2019, NASA officially declared the mission over. Opportunity had traveled 45.16 kilometers, a marathon plus a victory lap, on a world 300 million kilometers from home. These rovers were not just machines. They were explorers, pioneers, standing in for us on a world we could not yet reach ourselves. Their discoveries reshaped our understanding of Mars, proving that it was once a wetter, warmer, more dynamic world. Their perseverance, both the quality and the rover, inspired millions. Let us drift outward now, leaving the surface, rising into orbit, higher still, until Mars is a sphere hanging in the black. From this vantage, we can see the whole planet at once: the rust-red deserts, the white polar caps, the dark patches of volcanic rock, the swirling clouds of dust. Mars rotates below us, one full turn every 24 hours and 37 minutes. The terminator, the line between day and night, sweeps across the surface. On the day side, the sun illuminates the landscape, casting shadows, warming the ground. On the night side, temperatures plunge, frost forms, the thin air grows colder still. Seasons change. Spring comes to the southern hemisphere as Mars passes through perihelion. The south polar cap shrinks rapidly, sublimating carbon dioxide into the atmosphere. Dust devils spin up in the warming air, lifting particles into the sky. By summer, dust storms may grow, sometimes regional, occasionally global, wrapping the planet in a haze that can last for months. Autumn arrives, the storms subside, the air clears, winter approaches. carbon dioxide begins to freeze out of the atmosphere, forming a layer of frost on the South Polar Cap, thickening it, locking away a quarter of the planet's total atmospheric mass as ice. The Northern Hemisphere, meanwhile, experiences its mild summer, the polar cap there shrinking only slightly, because aphelion, the farthest point from the sun, occurs during northern summer. This seasonal cycle has repeated for billions of years, a rhythm as steady as a heartbeat, though the planet that beats this rhythm is dying, or rather has already died, and what we observe is the long, slow aftermath. But even in death, there is beauty. Even in silence, there is presence. Mars endures. It does not hurry. It does not cease. It simply is, a world of dust and stone and ice spinning through the dark, waiting. Waiting for what? Perhaps for us. Perhaps for nothing. Perhaps the question itself is meaningless, a projection of human hope onto an indifferent cosmos. Or perhaps Mars is a mirror, reflecting back to us our own capacity for wonder, for curiosity, for the desire to reach beyond ourselves and touch the unknown. There is a concept in science called deep time, the recognition that the Earth, and by extension, the universe, operates on timescales so vast that human lifespans are less than blinks in comparison. 1,000,000 years is a short interval in deep time. 1,000,000,000 years is substantial but not extraordinary. Mars has existed for 4.54 billion years, roughly the same age as Earth, formed from the same primordial disk of dust and gas. In that span, continents have risen and fallen on Earth, oceans have opened and closed, life has emerged, evolved, been nearly extinguished multiple times, and yet persisted. On Mars, in that same span, the magnetic field failed, the atmosphere bled away, the water vanished, and the surface froze. Two worlds, starting from similar conditions, diverging toward opposite fates. But deep time is not finished with either world. The Sun has another 5 billion years of stable life ahead before it exhausts the hydrogen in its core and begins to swell into a red giant. In that time, anything could happen. Mars could be terraformed by humans, made habitable again. Or it could remain as it is, a fossil of a world, a museum of planetary processes. Or something entirely unexpected could occur, some event we cannot predict because we do not yet understand all the variables at play. What we do know is that Mars has time. It is not in a hurry. It will be there, orbiting the Sun, for eons to come. Whether we visit, whether we settle, whether we leave it untouched, Mars will persist, patient and enduring, a red star in our night sky, a destination in our dreams. There is a phenomenon on Mars that has puzzled scientists since it was first observed. Recurring slope lineae, or RSL, are dark streaks that appear on steep slopes during the warmer months and fade during colder periods. They were first noticed in images from the Mars Reconnaissance Orbiter in 2011. The pattern was striking. The streaks grew downslope during late spring and summer, then faded in autumn and winter, only to reappear the following year in the same locations. The initial hypothesis was that these were caused by liquid water, perhaps briny water, with dissolved salts that lower the freezing point, allowing it to remain liquid even in the cold Martian environment. The idea was tantalizing. Liquid water flowing on the surface of Mars today, not billions of years ago, but right now. If true, it would be one of the most significant discoveries in planetary science. Spectroscopic analysis of the streaks showed the presence of hydrated salts, perchlorids, which supported the water hypothesis. But as more data came in, the picture became less clear. The streaks occurred in places where the subsurface temperature was too cold for even briny water to remain liquid. Alternative explanations emerged. Perhaps the darkening was caused by dry granular flows, sand or dust sliding down slopes, with the seasonal pattern driven by frost changing the surface properties. Or perhaps the hydrated salts absorbed water vapor from the atmosphere, not liquid water from below. As of now, the consensus leans away from flowing liquid water, though the debate is not entirely settled. The recurring slope lineae remain mysterious, a reminder that Mars continues to surprise us, to resist easy explanations, to demand careful observation and rigorous analysis. This is the nature of science. We form hypotheses based on limited data. We test them, we revise them, we admit when we are wrong. The process is messy, non-linear, filled with false starts and dead ends. But it is also the most reliable method we have for understanding reality. Mars teaches us humility. It reminds us that the universe does not owe us clarity, that understanding must be earned through patience and persistence. Let us consider the atmosphere of Mars more closely. It is thin, yes, just 6 millibars of pressure at the surface. But it is not static. It is dynamic, alive with processes that shape the environment. The atmosphere is 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and trace amounts of oxygen, water vapor, and other gases. This composition is very different from Earth's atmosphere, which is 78% nitrogen and 21% oxygen. Carbon dioxide dominates because Mars lacks the processes that remove it. On Earth, carbon dioxide is absorbed by oceans, locked into limestone by marine organisms, buried in sediments, and recycled through plate tectonics. Mars has no oceans, no tectonic activity, so carbon dioxide released by volcanoes accumulates in the atmosphere. But the atmosphere is so thin that even though carbon dioxide is the dominant gas, it does not create a strong greenhouse effect. The surface pressure is simply too low. Water vapor is present in tiny amounts, typically around 0.03%, but it plays a crucial role. Even this small amount can form clouds, thin wisps of water ice crystals that drift across the Martian sky. These clouds are most common near the poles and in the mornings when temperatures are coldest. They are delicate, ephemeral, but they are there, a reminder that Mars still has a water cycle, albeit a muted one. Dust is the other major component of the Martian atmosphere. Not a gas, but suspended particles that color the sky, scatter the sunlight, and sometimes grow into planet-wide storms. Martian dust is incredibly fine, about 1.5 microns in diameter on average, smaller than talcum powder. It is lifted by wind and by dust devils, convective vortices that spin across the plains, visible as columns of swirling dust. Dust devils are common on Mars, more common than on Earth, because the thin atmosphere heats and cools more rapidly, creating strong temperature gradients that drive convection. Rovers have been struck by dust devils, felt the brief drop in air pressure as the vortex passed overhead. Sometimes, by chance, a dust devil clears the dust from a rover's solar panels, extending the mission's life. Spirit, Opportunity, and the earlier Pathfinder mission all benefited from these fortuitous cleaning events, gifts from the Martian wind. But dust can also be deadly. The global dust storm of 2018 that ended Opportunity's mission is a stark reminder. These storms begin locally, usually in the southern hemisphere during southern spring or summer. Dust lifted into the atmosphere absorbs sunlight, warming the air, creating stronger winds, lifting more dust. The storm grows, feeding on itself, a positive feedback loop. Within weeks, the entire planet can be engulfed, the atmosphere choked with dust, the surface shrouded in twilight. During such storms, surface temperatures drop because sunlight is blocked, but atmospheric temperatures rise because the dust absorbs solar energy. The wind speeds increase, though on Mars, even a strong wind is not dangerous to solid objects like rovers or future habitats. The atmosphere is so thin that a 100 km/h wind on Mars exerts the same force as a 10 km/h breeze on Earth. The danger is not the wind itself, but the dust it carries, the darkness it creates, the power it denies to solar panels. Night on Mars is cold and clear, at least when dust storms are not raging. The stars blaze overhead, undimmed by city lights, unpolluted by a thick atmosphere. The Milky Way stretches across the sky, a river of light, brighter than most humans on Earth have ever seen. Constellations are the same as viewed from Earth because the distance between the two planets is negligible compared to the distance to the stars. Orion still hunts, Ursa Major still circles the pole, Scorpius still arcs across the summer sky. But there are differences. Earth does not hang in the Martian sky the way the moon hangs in ours, because Mars has no tidally locked companion pointing always at one face. Earth is a wandering star, a bright blue point of light that moves through the constellations, sometimes visible in the morning sky, sometimes in the evening, sometimes lost in the glare of the sun. From Mars, Earth and the Moon appear close together, the Moon a fainter companion to the brighter Earth, like a double star. Phobos and Deimos rise and set, though, as we discussed, Phobos moves in the opposite direction to most celestial objects, a strange and unsettling sight if you are used to Earth's sky. Deimos is slower, more sedate, less intrusive. Both are dim, not bright enough to cast noticeable shadows, not significant sources of light. The stars do not twinkle on Mars. Twinkling, or stellar scintillation, is caused by turbulence in Earth's thick atmosphere, pockets of warmer and cooler air bending light in random patterns. Mars's atmosphere is too thin to produce this effect. Stars shine steady, points of light unwavering, like diamonds on black velvet. If you stood on Mars at night, far from any habitat, with no lights to mar the darkness, you would feel the weight of the cosmos pressing down, not oppressively, but with a kind of gentle insistence. You would feel small, yes, but also connected, part of a universe so vast that comprehension fails, yet so ordered that patterns emerge, that laws hold, that understanding is possible. This is the gift of Mars. It places us in context. It shows us our scale. It reminds us that we are children of the cosmos, made of the same elements forged in the hearts of stars, standing on a world that was molten rock 4 billion years ago, gazing up at light that left distant suns centuries or millennia past. In that gaze, in that recognition, there is both humility and exaltation. The question of life on Mars is not settled. We have not found it, but we have not disproven its existence either. The Viking landers in the 1970s ran experiments designed to detect microbial life. One experiment, the labeled release, added nutrients to Martian soil and monitored for gases that would indicate metabolism. The results were positive. Gas was released. But a control experiment that heated the soil to sterilize it also produced gas, suggesting a chemical rather than biological process. The scientific community was divided, but the majority opinion leaned toward non-biological explanations. Since then, no mission has carried life detection experiments, though that is about to change. Future missions are planned with more sophisticated instruments, better able to distinguish biological from non-biological processes. But the fundamental challenge remains. Life may not exist on the surface, where radiation and oxidizing chemicals make survival difficult. Life, if it exists, is likely deep underground, in aquifers, in pockets of warmth and water, places we cannot yet reach with rovers. Another possibility is that life once existed on Mars, but is now extinct. The planet's early history, during the Noachian period, may have been conducive to life. Water was abundant, the atmosphere was thicker, temperatures were warmer. If life arose during that time, it might have persisted for hundreds of millions of years before the changing conditions drove it to extinction. Fossils might remain, microbial mats preserved in ancient rocks, chemical signatures locked in minerals. Finding such fossils would require careful searching, sophisticated analysis, and a great deal of luck. Perseverance is collecting samples with this possibility in mind, choosing rocks that formed in ancient water that might contain organic molecules or structural features indicative of biology. But even with the best instruments, interpreting such evidence is difficult. Organic molecules can form through non-biological processes. Structures that look like fossils can be geological artifacts. The burden of proof is high, as it should be. Extraordinary claims require extraordinary evidence. There is also the unsettling possibility that Earth and Mars exchanged life in the distant past. Meteorite impacts can blast rocks from one planet into space. Some of those rocks, over millions of years, cross the gap between the worlds and fall onto the other planet. We have Martian meteorites on Earth, dozens of them. Rocks ejected from Mars by impacts, drifting through space, eventually captured by Earth's gravity and falling as meteorites. Some of these meteorites are very old, dating back to the time when Mars was wetter and warmer. If microbes existed on Mars during that time, could they have survived the journey to Earth? The answer is maybe. Experiments have shown that certain hardy microbes, like tardigrades or endospores, can survive the vacuum of space, the cold, the radiation, if they are shielded inside a rock. The impact that ejects the rock generates tremendous heat, but the interior of a large enough fragment might remain cool. The journey through space is long, but some microbes can remain dormant for millions of years. Re-entry into Earth's atmosphere generates heat, but again, the interior of a meteorite can stay cool. So it is possible. Not likely, but possible. If this happened, if life was transferred from Mars to Earth, or vice versa, then discovering life on Mars would not answer the question of whether life arises commonly in the universe. We would have to determine whether Earth life and Mars life share a common origin, which would suggest panspermia, or whether they arose independently, which would suggest that life emerges wherever conditions allow. This is one of the most profound questions we can ask. Are we alone, or is life common? Mars, our nearest neighbor with a history of habitability, is the best place to begin searching for an answer. There is a subtle beauty to the way sunlight falls on Mars. The distance from the sun means that solar energy reaching the Martian surface is only about 43% of what Earth receives. The sun appears smaller, 2/3 the diameter, less intense. Shadows are softer, the light more diffuse, especially when dust is suspended in the atmosphere. At dawn, the sun rises slowly, the sky brightening from black to deep purple to salmon pink. The transition is gradual, gentle, not the sudden burst of light we experience on Earth. Frost that formed during the night begins to sublimate, not melting but going directly from ice to vapor, leaving no puddles, just a faint haze near the ground that dissipates as the air warms. Midday on Mars is the warmest time, though warm is relative. Near the equator in summer, surface temperatures can reach 20 degrees Celsius, above freezing, comfortable by Martian standards. But even then, the air temperature remains well below zero because the thin atmosphere cannot hold heat. A thermometer in the sun might read 15 degrees, while one in the shade reads -50. The difference is stark, a consequence of that thin blanket of air that does so little to moderate temperatures. Afternoon brings the possibility of dust devils, those swirling columns that march across the plains, sometimes dozens visible at once. They are hypnotic to watch, graceful and aimless, wandering wherever the convective currents take them. Rovers have photographed their own shadows as dust devils pass nearby, the shadow rippling and distorting as the vortex moves through. Sunset on Mars is when the sky performs its most famous trick. As the sun approaches the horizon, the sky around it turns blue, a small patch of azure in an otherwise butterscotch sky. This is because the dust particles in the atmosphere scatter red light more efficiently than blue light, the opposite of Earth's atmosphere where air molecules scatter blue light. On Mars, the blue light passes straight through the dust near the sun, reaching your eye, while the red light is scattered away. The result is that brief moment of blue surrounding the setting sun, a reversal of Earth's red sunsets, a reminder that you are standing on an alien world where familiar rules are inverted. As the sun sets fully, the sky fades quickly from pink to purple to black. Twilight is short because there is so little atmosphere to scatter light once the sun is below the horizon. Stars appear, sharp and steady. The temperature plummets. Frost begins to form. The Martian day is over, and the long, cold night begins. The geology of Mars rewards close attention. Every rock tells a story. Every crater records an impact. Every dune represents the accumulated work of wind over millennia. The surface is not uniform. It is a patchwork of different ages, different processes, different histories. The oldest surfaces in the southern highlands are Noachian, 4 billion years old or more, cratered and weathered, the scars of the late heavy bombardment still visible. This was a period about 4 billion years ago, when the inner solar system was pelted by asteroids and comets, a final clearing of debris left over from the planet-building era. Earth's surface from that time has been erased by tectonics and erosion, but Mars preserves the record, frozen in stone. The northern lowlands are younger, Hesperian, or even Amazonian in age. The Amazonian period, named after Amazonis planitia, a smooth plain in the northern hemisphere, extends from 3 billion years ago to the present. It is the current epoch of Martian history, characterized by low rates of geological activity, slow erosion, and the gradual accumulation of dust. Between these ancient highlands and younger lowlands lies the dichotomy boundary, a transition zone that is itself geologically interesting. Some areas show evidence of ancient shorelines, terraces that might have marked the edge of a northern ocean. This hypothetical ocean, sometimes called Oceanus Borealis, would have covered much of the northern lowlands during the Noachian, a body of water potentially as large as Earth's Arctic Ocean. The evidence is suggestive, but not definitive. The terraces could also be geological features formed by other processes. The debate continues. Lava plains cover vast areas of Mars, the product of eruptions from Tharsis, Elysium, and other volcanic regions. These flows are basaltic, dark, and dense, rich in iron and magnesium. They are similar to the lava that forms Earth's oceanic crust and the Hawaiian Islands, low viscosity magma that flows easily, spreading out in thin sheets that pile up over time. The most recent lava flows on Mars are geologically young, just a few million years old, a blink in geological terms. This suggests that Mars is not entirely dead, that magma chambers still exist deep below the surface, that future eruptions are possible. We have not witnessed one yet, and we may not for millennia or longer, but the potential is there. Dust on Mars is more than just a nuisance. It is a defining characteristic of the planet, as fundamental to its identity as the red color itself. Martian dust is iron-rich, oxidized, rust particles ground down to microscopic size by billions of years of impacts and wind erosion. It covers everything, a ubiquitous layer that coats the rocks, fills the low-lying areas, suspends in the atmosphere, colors the sky. The dust is electrostatically charged, which makes it cling to surfaces. Rovers and landers find their solar panels gradually darkening as dust accumulates, reducing power generation. This was a significant concern for Spirit and Opportunity, which relied entirely on solar power. Engineers predicted the missions would end when dust accumulation reduced power below operational levels. The dust devils that occasionally cleaned the panels were unplanned gifts, extending the missions far beyond their design lifetimes. Curiosity and Perseverance, being nuclear-powered, do not have this concern. Their radioisotope thermoelectric generators convert heat from decaying plutonium into electricity, independent of sunlight. This allows them to operate through dust storms, through winter, through the Martian night, without worrying about power. Dust storms on Mars range in size from local devils to regional storms to the rare but spectacular global events that engulf the entire planet. The mechanisms that trigger global storms are not fully understood. They tend to occur during southern summer, when Mars is closest to the sun and surface heating is strongest. But not every southern summer produces a global storm. The last major one was in 2018. Before that, 2007 and 2001. Before that, the 1970s and 1950s. The pattern is irregular, unpredictable, another mystery Mars holds close. When a global storm occurs, it transforms the planet. The dust-laden atmosphere becomes opaque, blocking most sunlight from reaching the surface. Temperatures drop at ground level, but rise in the upper atmosphere as the dust absorbs solar energy. The wind intensifies, lifting more dust, perpetuating the storm. Eventually, the dust begins to settle, too heavy to remain aloft despite the winds. The storm clears, the sky brightens, and Mars returns to normal. The cycle can take months. For future human explorers, dust will be both a challenge and a resource. It will infiltrate habitats, clog filters, coat equipment, but it also contains iron, silicon, oxygen, and other elements useful for manufacturing. Techniques are being developed to sinter Martian regolith, using heat to fuse the particles into solid blocks that can be used as construction material. Dust, the bane of rovers, might become the foundation of Martian infrastructure. There is something deeply moving about the scale of human effort that has been directed toward understanding Mars. Dozens of missions spanning more than 5 decades, thousands of scientists and engineers dedicating their careers to studying a world none of them will ever visit. Billions of dollars invested in robots and orbiters and landers, all in pursuit of knowledge, of answers to questions about how planets evolve, whether life exists beyond Earth, what our place is in the cosmos. This is humanity at its best, not competing for resources, not fighting over territory, but reaching outward, driven by curiosity, by wonder, by the desire to know. The missions to Mars are international collaborations, data shared openly, discoveries celebrated collectively. When Perseverance landed in Jezero crater, people around the world watched, cheered, felt pride and joy regardless of nationality. For a moment, we were united in awe at what we had accomplished together, and the work is far from over. New missions are in development. The European Space Agency and Roscosmos, the Russian Space Agency, are planning ExoMars, a mission to drill up to 2 meters below the surface, deeper than any previous mission, searching for organic molecules preserved in the subsurface. NASA and ESA are collaborating on the Mars Sample Return Campaign, the complex multi-mission effort to bring Perseverance's samples back to Earth for detailed analysis. Japan's space agency, JAXA, is studying a mission to Phobos to land on the Moon, collect samples, and return them to Earth. Phobos has never been visited up close, and samples from it could reveal whether it is a captured asteroid or a piece of Mars blasted into orbit by an ancient impact. Private companies are entering the arena. SpaceX's Starship is being designed with Mars in mind, a fully reusable spacecraft capable of carrying large payloads and eventually humans to the Martian surface. Elon Musk has stated his goal of establishing a self-sustaining city on Mars, a vision that is audacious, controversial, but not impossible. The technology is being developed. The challenges are known. The timeline is uncertain, but the trajectory is clear. Within the next 20 to 30 years, humans will likely set foot on Mars. That first landing will be a historical moment, on par with the moon landing in 1969, perhaps even more significant, because Mars is not just a destination, but a potential second home. The first humans on Mars will not plant a flag and leave. They will stay, establish a base, begin the long work of understanding and adapting to the new world. And what then? Will we terraform Mars, warm it, thicken its atmosphere, melt its ice, turn it green with life? Or will we live in habitats, preserving Mars as it is, treading lightly, taking nothing but knowledge, leaving nothing but footprints? These decisions have not been made. They will be debated, fought over, decided by future generations. Our role now is to continue exploring, to gather the data that will inform those decisions, to ensure that when the time comes, we act wisely, with respect for the planet and for any life it might harbor, past or present. There is a loneliness to Mars that is hard to articulate. It is a world without voices, without movement, except the slow drift of dust and the patient rotation of the planet itself. No birds call, no insects hum, no wind whispers through trees because there are no trees. The silence is absolute in a way that Earth can never be. Even in the quietest desert or the deepest cave, there is sound, your heartbeat, your breath, the creak of rock settling, the distant rumble of Earth's living interior. On Mars, the silence is deeper. The ground does not quake with tectonic activity. The core is solid, inert. The wind, when it blows, carries so little force through the thin air that it barely registers. The loneliness is not oppressive, but it is present, a reminder that this is a world that has finished its story, that lives now in epilogue, waiting for whatever comes next. And yet, there is a peace in that loneliness, a stillness that invites contemplation. Standing on Mars, you would be farther from home than any human has ever been. Earth would be a pale blue dot in the sky, barely distinguishable from the background stars. You would be, in a very real sense, alone in a way that is impossible to be on Earth, where even in the remotest wilderness, you are still on the same planet as 8 billion other humans. That solitude might be frightening. It might also be liberating. It depends, perhaps, on what you carry within you, whether you see isolation as exile or as freedom. The astronauts who go to Mars will need to be comfortable with both, to embrace the adventure while acknowledging the weight of separation. But they will not be entirely alone. Earth will still be there, messages traveling back and forth at the speed of light, taking anywhere from 4 to 24 minutes, one way, depending on the planet's positions. Conversations will be impossible in real time, each exchange requiring patience, each question followed by long silence before the answer arrives. But communication will persist, a thread connecting the explorers to home, reminding them that they are not forgotten, that their mission matters, that humanity watches and waits. Let us talk about water on Mars in greater detail, because water is the key to everything. Where there is water, there is the potential for life as we know it. Where there is water, there is a resource for future human settlement. Where there was water, there is a story to uncover about climate change, atmospheric loss, and planetary evolution. We have already discussed the valley networks, the dried lake beds, the evidence written in stone that water once flowed freely on the Martian surface. But how much water? Estimates vary, but some studies suggest that ancient Mars might have held enough water to cover the entire planet to a depth of 100 to 1,000 meters. Not all of that water would have been on the surface at once. Much of it would have been locked in polar caps, in glaciers, in subsurface ice, just as Earth's water is distributed across oceans, ice caps, groundwater, and atmosphere. Where did all that water go? Some of it is still on Mars, frozen at the poles and in the subsurface. Some of it was broken apart by solar ultraviolet radiation into hydrogen and oxygen. The hydrogen, being light, escaped into space. The oxygen combined with iron in the rocks, forming the rust that gives Mars its color. Some water was lost to the solar wind, ionized and stripped away, when the magnetic field failed. NASA's MAVEN mission has measured the current rate of water loss. The numbers are small on human timescales, about 100 grams per second, but accumulated over billions of years, they add up. MAVEN has also shown that the loss rate increases dramatically during solar storms, when the solar wind intensifies and the stripping becomes more efficient. This suggests that early in Martian history, when the sun was younger and more active, producing more frequent and intense storms, the water loss would have been even faster. But there is still water on Mars today, and in surprising quantities. Radar measurements from orbit have mapped subsurface ice across vast swathes of the mid-latitudes. In some places, the ice begins just centimeters below the surface. In others, it is meters deep, mixed with rock and dust, forming a permafrost layer similar to what we find in Earth's polar regions. This ice is not ancient surface water that froze in place. It is relatively young, perhaps deposited within the last few million years during periods when Mars's axial tilt was greater than it is now. Mars's obliquity, the angle between its rotational axis and the plane of its orbit, varies over timescales of tens to hundreds of thousands of years, ranging from about 15 degrees to 35 degrees. Earth's obliquity is stabilized by the Moon's gravitational influence, varying only between about 22 and 24 degrees. Mars, lacking a large stabilizing moon, experiences wilder swings. When Mars's obliquity increases, the poles receive more direct sunlight, warming them, causing ice to sublimate. The water vapor enters the atmosphere, is transported by winds, and refreezes at lower latitudes, accumulating as ice in the soil. When the obliquity decreases, the process reverses, and the mid-latitude ice sublimates, migrating back toward the poles. This cycle has repeated many times, leaving layers of ice at different depths, a frozen record of climate variations. For future explorers, this ice is a treasure, accessible, widespread, waiting to be extracted. Habitats could be placed near these ice deposits, reducing the need to transport water from Earth. A single cubic meter of Martian regolith in these ice-rich regions might contain several hundred kilograms of water. Heat the soil, collect the vapor, condense it, purify it. The process is straightforward. The technology already exists. Mars has inspired not just scientists, but artists, writers, musicians, filmmakers. The planet has served as a canvas for human imagination, a place to project our hopes and fears, our dreams of exploration, and our anxieties about the unknown. From the canals of Percival Lowell to the terraformed paradise of Kim Stanley Robinson's Mars trilogy, from the hostile environment of The Martian to the ancient ruins imagined in countless tales, Mars has been a mirror reflecting our culture back to us. There is something about Mars that captures the imagination in a way that Venus or Jupiter do not. Perhaps it is the visibility, the fact that Mars shines brightly in our night sky, accessible to the naked eye, a constant presence throughout human history. Perhaps it is the surface, solid and potentially walkable, unlike the crushing atmosphere of Venus or the gas giant nature of Jupiter. Perhaps it is the similarities to Earth, the day length, the seasons, the polar ice caps, features that make Mars feel almost familiar, almost reachable. Or perhaps it is the tragedy. Mars was once Earth-like, and now it is not. That transformation, that loss, resonates with us. It is a warning, a cautionary tale about what can happen when a planet's environment degrades beyond a certain threshold. It is also a challenge, a question. Can we reverse that degradation? Can we bring Mars back to life? Can we demonstrate mastery over planetary processes in a way that redeems rather than destroys? The ethical dimensions of this question are profound. If we terraform Mars, we are making a decision that will affect the planet for millions of years. We are imposing our will on a world that has existed for 4.5 billion years, changing it to suit our needs. Do we have that right? Does Mars have intrinsic value that should be preserved? Or is it merely a resource to be used? Some argue that Mars is already dead, that there is no harm in modifying it because there is nothing left to harm. Others counter that even a dead world has value, that the geological record is a scientific treasure that should be preserved, that any native life, even if only microbial and buried deep underground, has a right to exist free from contamination by Earth organisms. There is also the practical consideration. We do not yet know enough about Mars to make an informed decision about terraforming. We have explored only tiny fractions of the surface. We have not drilled deep enough to sample the subsurface thoroughly. We have not definitively answered the question of whether life exists there now or existed in the past. Rushing into planetary scale engineering before we understand the system we are engineering would be hubris, a repetition of the mistakes we have made on Earth, where we altered ecosystems without understanding them and suffered unintended consequences. The wise path forward is patience. Explore thoroughly, search for life exhaustively, understand the planet's systems completely, then, and only then, with full knowledge and broad consensus, make the decision about what to do next. Mars has waited for billions of years. It can wait a few more decades or centuries while we do our homework. Let us travel back in time once more to a specific moment in Martian history, 3.7 billion years ago, late in the Noachian period. The magnetic field has already weakened significantly, though it has not yet disappeared entirely. The atmosphere is thinning, the pressure dropping, the greenhouse effect waning. Temperatures are cooler than they were a few 100 million years earlier, but liquid water still exists on the surface, in lakes, in rivers, perhaps in a northern ocean. This is a critical moment, a turning point. Life, if it arose on Mars, would have done so by now. The conditions were more favorable earlier, during the first few 100 million years, when volcanic activity was intense, when hydrothermal systems churned, when organic molecules were being delivered by comets and asteroids. By 3.7 billion years ago, life would have had time to establish itself, to spread, to diversify. But the environment is deteriorating. The atmosphere is leaking into space. Water is freezing or evaporating. Any life present would be facing increasing stress, forced to adapt or retreat into more hospitable niches. This is when organisms might have migrated underground, seeking refuge in aquifers, in pore spaces in the rock, in geothermal hotspots where energy and liquid water still coexisted. On Earth, life arose remarkably quickly, within the first few 100 million years of the planet's existence. By 3.5 billion years ago, microbial mats were forming stromatolites, layered structures built by communities of bacteria. Photosynthesis had evolved. Life was already complex, already diverse. If the same rapid emergence occurred on Mars, then by 3.7 billion years ago, Martian life would have been well established, perhaps even approaching the complexity of early Earth life. But then, the environment collapsed. Over the next few 100 million years, Mars transitioned from a wet world to a dry one, from a warm world to a cold one, from a potentially habitable world to the frozen desert we see today. Life, if it existed, would have been driven to extinction except in those deep refugia where conditions remain stable. This is speculation, of course. We have no evidence of Martian life, past or present. But the scenario is plausible, grounded in what we know about planetary evolution and the resilience of life. And if it happened, if Mars once harbored a biosphere that was lost when the environment changed, then the planet is not just a geological curiosity, but a graveyard, a memorial to what was and what could have been. The surface of Mars is bombarded by radiation. Without a thick atmosphere and without a magnetic field, cosmic rays and solar particles strike the ground with little attenuation. Cosmic rays are high-energy particles, mostly protons, that originate from supernovae and other energetic events in the galaxy. They travel at nearly the speed of light and carry enough energy to penetrate several meters into rock. Solar particles are less energetic, but more numerous, a constant stream from the Sun. During solar flares and coronal mass ejections, the flux increases dramatically. On Earth, our magnetosphere and atmosphere protect us, absorbing and deflecting this radiation. On Mars, there is no such protection. For future human explorers, this is a serious challenge. Prolonged exposure to Martian surface radiation levels would increase cancer risk, damage cells, and potentially cause acute radiation sickness if a particularly strong solar event occurred while astronauts were outside. Habitats will need shielding, either built underground, covered with meters of regolith, or constructed from materials that block radiation effectively. Water is an excellent radiation shield. Hydrogen atoms in water molecules are effective at absorbing and scattering radiation. A habitat surrounded by water tanks, serving the dual purpose of storage and shielding, could reduce radiation exposure significantly. Ice mixed with regolith, the Martian permafrost, also provides good shielding. Digging into the ground and building habitats partially underground is likely the most practical solution. For any life that might exist in the Martian subsurface, radiation is less of a concern. Below a few meters of rock or ice, the radiation dose drops to levels that hardy microbes could tolerate. On Earth, subsurface microbes thrive in environments with naturally high radiation, in uranium-rich rocks, in deep boreholes, demonstrating that life can adapt to radiation if given evolutionary time. But on the surface, radiation is a sterilizing force. Any organic molecules, any biological structures, any potential fossils are gradually degraded by the constant bombardment. This is why searching for signs of past life requires drilling, excavating, looking beneath the surface where organics might be preserved, protected from the destructive rain of particles from above. The rocks of Mars tell stories in a language we are learning to read. Each mineral, each texture, each chemical signature is a word, a sentence, a paragraph in the narrative of the planet's history. Rovers carry instruments to read this language, spectrometers to identify chemical elements, cameras to capture texture and structure, drills to extract samples from depth, lasers to vaporize rock, and analyze the resulting plasma. One of the most important instruments is the alpha particle X-ray spectrometer, or APXS, which measures the elemental composition of rocks and soil. It works by bombarding a sample with alpha particles and X-rays from a small radioactive source, then measuring the energy of particles and X-rays that bounce back or are emitted by the sample. Different elements produce characteristic signatures, allowing scientists to determine what the rock is made of. Another key tool is the ChemCam laser on Curiosity, which fires a powerful infrared laser at rocks up to 7 meters away, vaporizing a tiny amount of material. The vaporized rock glows as plasma, and the light from that plasma is analyzed by a spectrometer. Each element emits light at specific wavelengths, creating a unique spectral fingerprint. In just a few seconds, ChemCam can tell you what a rock is made of without ever touching it. Perseverance carries an upgraded version called SuperCam, which adds additional capabilities: Raman spectroscopy to identify minerals, infrared spectroscopy to detect organic molecules, and a microphone to record the sound of the laser impacts. The microphone also records wind, the crunch of the rover's wheels on regolith, and the whir of the helicopter Ingenuity as it flies nearby. For the first time, we can hear Mars, not just see it. The data from these instruments accumulates slowly. Each rock studied, each drill hole sampled, each measurement taken adds a small piece to the puzzle. Over years and decades, the pieces connect, patterns emerge, and our understanding deepens. This is slow science, patient science, requiring attention to detail and a willingness to embrace uncertainty. Sometimes the data surprises us. Curiosity found manganese oxide in some rocks, a mineral that on Earth typically forms in oxygen-rich environments. Mars's atmosphere has almost no oxygen. How did manganese oxide form? Perhaps the ancient Martian atmosphere was more oxygen-rich than we thought, possibly produced by photosynthetic organisms, though that is highly speculative. Or perhaps it formed through non-biological processes we do not yet understand. The mystery remains open. Perseverance found organic molecules in several rocks in Jezero crater, preserved for billions of years. Organic molecules are not evidence of life. They can form abiotically through various chemical processes, but they are a necessary ingredient for life as we know it, and finding them preserved in ancient lake sediments is tantalizing. The molecules will be analyzed more thoroughly once the samples are returned to Earth, where laboratories can perform tests impossible on Mars. There is a place on Mars called the Medusae Fossae Formation, a massive deposit of easily eroded material stretching along the equator. It is among the largest volcanic deposits in the solar system, covering an area comparable to India, with a volume estimated at 2.6 million cubic kilometers. The material is thought to be volcanic ash, possibly from explosive eruptions billions of years ago, or wind-blown dust that has compacted over time. What makes the Medusae Fossae Formation interesting is its texture. It is soft, easily eroded by wind, sculpted into strange formations, cliffs and mesas and yardangs that look almost organic. Images from orbit show features that resemble melted wax, frozen mid-flow. Up close, rovers have never visited, but the terrain appears loose, dusty, challenging to traverse. Radar studies have revealed something unexpected. The formation is incredibly porous, possibly 15% air by volume, like a sponge. This suggests that the material was deposited rapidly, not compacted by the weight of overlying layers, possibly from explosive volcanic eruptions that sent clouds of ash into the atmosphere, which then settled out over vast areas. If the Medusae fossae formation is indeed volcanic ash, it would have had profound effects on the Martian climate when it was deposited. Ash in the atmosphere blocks sunlight, cooling the surface, potentially triggering ice ages. But volcanic eruptions also release gases like sulfur dioxide and carbon dioxide, which can enhance the greenhouse effect and warm the planet. The interplay of these effects would have made Martian climate highly variable, swinging between warm and cold periods depending on the intensity and frequency of eruptions. This is another reminder that Mars's climate history is not simple. It is not a steady decline from warm and wet to cold and dry, but a complex story with fluctuations, brief episodes of warmth even during the overall cooling trend, regional variations, feedback loops that amplified or damped changes. Reconstructing this history requires integrating data from geology, atmospheric science, modeling, and careful interpretation. It is detective work on a planetary scale. There is comfort in the predictability of Mars's orbit. Every 687 Earth days, Mars completes one orbit around the Sun. Every 26 months, Earth and Mars reach opposition, the point where Earth is between the Sun and Mars, bringing the two planets closest together. These close approaches are when we launch missions, taking advantage of the reduced distance to minimize travel time and fuel requirements. The Hohmann transfer orbit, the most energy-efficient path between Earth and Mars, takes about 6 to 9 months, depending on the specifics of the planetary positions. During that time, the spacecraft coasts through the vacuum, unpowered, except for occasional corrections, covering hundreds of millions of kilometers in silence. The astronauts who make that journey will experience isolation unlike anything we have known. The International Space Station orbits just 400 kilometers above Earth. The Moon is 384,000 kilometers away. Mars, at its closest, is 55 million kilometers distant. Communication delays of up to 22 minutes one way mean that any emergency must be handled by the crew alone. Mission Control can advise, but they cannot react in real time. The astronauts will be truly on their own. Psychologically, this is challenging. Training programs are studying how crews cope with isolation, confinement, and the knowledge that they are utterly dependent on their spacecraft and each other. Analog missions in Antarctica, in underwater habitats, in simulated Mars bases in deserts, provide data but cannot fully replicate the experience. The real test will come when the first crew leaves Earth orbit and begins the long coast to Mars, watching their home planet shrink to a point of light, knowing that there is no turning back, that the only way forward is through. But humans are adaptable. We have crossed oceans in wooden ships, not knowing what lay on the other side. We have ventured into polar regions, into jungles, into mountains, into the deep sea. We have sent 12 people to the surface of the Moon and brought them all home safely. We can do this. It will require courage, preparation, and a willingness to accept risk, but it is within our capability. Let us consider the economics of Mars exploration and settlement. Space missions are expensive. Curiosity cost about $2.5 billion. Perseverance cost about $2.7 billion. The Mars Sample Return Campaign, still in planning, is estimated to cost several billion more. These are substantial investments, justified by the scientific return, but difficult to sustain indefinitely. For Mars to transition from a scientific curiosity to a destination for permanent human presence, the economics must change. There must be reasons beyond science to go, resources to extract, products to create, value to return. Otherwise, Mars settlement will remain a government-funded project, vulnerable to budget cuts and political whims. What does Mars offer economically? Not minerals in the traditional sense. The cost of transporting material from Mars to Earth is prohibitive. Nothing found on Mars, not gold, not diamonds, not rare earths, could justify the expense of shipping it to Earth when the same materials can be obtained here for less. But Mars offers location. It is a base for exploring the asteroid belt, where valuable metals like platinum and nickel exist in abundance. It is a place to build spacecraft, using Martian resources, reducing the need to lift everything from Earth's deeper gravity well. It is a research outpost, where scientists can study the planet up close, conduct experiments impossible on Earth, search for life with human intuition and flexibility. And perhaps most importantly, Mars offers an insurance policy. Humanity is currently confined to one planet, vulnerable to any catastrophe that affects Earth. An asteroid impact, a supervolcanic eruption, a nuclear war, a pandemic worse than any we have experienced could threaten our survival as a species. A self-sustaining colony on Mars would ensure that even if Earth were devastated, humanity would continue. This argument resonates with some, but not others. Critics point out that making Mars habitable is far more difficult than preserving Earth's habitability, that resources spent on Mars settlement could be used to address problems here. Both perspectives have merit. The choice is not binary. We can work to protect Earth while also taking steps toward becoming a multi-planetary species. The two goals are not mutually exclusive. Imagine Mars a century from now. Perhaps several hundred people live there, in a base near the equator, in habitats partially buried under regolith, their walls lined with water tanks for radiation shielding. Solar panels and small nuclear reactors provide power. Greenhouses glow with LED lights, growing lettuce, tomatoes, strawberries, soybeans. The food is supplemented with supplies from Earth, shipped every 2 years during launch windows. But the goal is self-sufficiency, producing as much as possible locally. The inhabitants are scientists, engineers, technicians, people who volunteered for a one-way trip, or at least a commitment measured in years. They work on research projects, maintaining the base, expanding the infrastructure. They explore the surrounding terrain in pressurized rovers, drilling for ice, collecting samples, setting up instruments. Life is regimented, every day scheduled, every resource accounted for. Water is recycled endlessly, almost nothing wasted. The air is scrubbed of carbon dioxide, oxygen replenished by electrolysis of water. Waste is composted or incinerated, their ashes mixed with regolith to make soil for the greenhouses. Everything has a purpose. Nothing is disposable. But there are moments of beauty. Watching sunrise through a viewport, the sky shifting from black to pink. Eating a fresh tomato, the first harvest from a new greenhouse section. Video calls with family on Earth. The delay frustrating, but the connection precious. Walking on the surface in a suit. feeling the crunch of regolith beneath your boots, looking up at stars that do not twinkle. Challenges are constant. Equipment breaks, dust infiltrates seals, someone gets sick, and the limited medical facilities are stretched. A solar storm forces everyone into the most heavily shielded part of the base for 2 days. A resupply mission is delayed due to technical problems, stretching food reserves. But the colony persists, adapts, survives, and slowly, very slowly, it grows. A second base is established 500 kilometers away, near a different scientific site. Communication links are set up. Rovers travel between the bases, carrying supplies, personnel, messages. The Martian population reaches 500, then 1,000. Children are born, the first humans who will grow up under Martian gravity, who will think of Mars as home. This is not science fiction. This is extrapolation, careful projection of current technology and trends. Everything described is possible with existing knowledge. The challenges are engineering, not physics. It will be difficult, yes. It will be expensive. People will die. Accidents will happen. Setbacks will occur. But it can be done. And if humanity chooses to do it, it will be done. Let us pull back now, rising above Mars, above the solar system, looking at the broader context. Our solar system formed 4.567 billion years ago from a collapsing molecular cloud, a dense region of gas and dust within the galaxy. The collapse was likely triggered by a nearby supernova, the shock wave compressing the cloud until gravity took over and pulled it inward. As the cloud collapsed, it began to spin, flattening into a disk. The center grew hotter and denser until nuclear fusion ignited and the sun was born. In the disk around it, particles stuck together, growing into pebbles, boulders, kilometer-sized planetesimals, and eventually planets. This process occurred over millions of years, a chaotic dance of collisions and accretion. Some objects grew large enough to become planets. Others remained small, becoming asteroids or comets. Mars, as we have discussed, formed in a region where material was sparse, which limited its growth. But Mars is part of a larger story. It is one of 8 planets, or 4 if you count only the rocky terrestrial worlds: Mercury, Venus, Earth, Mars. These 4 worlds share a common origin, but diverge dramatically. Mercury, closest to the Sun, was stripped of much of its outer layers by the intense heat, leaving a dense iron core covered by a thin rocky mantle. Venus, Earth's twin in size, developed a runaway greenhouse effect, its surface baked to temperatures hot enough to melt lead. Earth found the Goldilocks zone, not too hot, not too cold, with liquid water and life. Mars, as we have discussed, lost its atmosphere and water, becoming the cold desert it is today. Why did these 4 worlds, starting from similar conditions, end up so different? The answer lies in the details. Distance from the Sun, mass, presence or absence of a magnetic field, impact history, volatile delivery, atmospheric composition. Small differences in initial conditions, amplified over billions of years, led to vastly different outcomes. This is a fundamental insight of planetary science, and it has implications for the search for life beyond our solar system. We have discovered thousands of exoplanets, worlds orbiting other stars. Some are rocky, some are gas giants, some orbit in their star's habitable zone, where liquid water could exist on the surface. But habitability is not just about distance from the star. It depends on magnetic fields, atmospheric retention, tectonic activity, volatile inventory, and countless other factors. A planet can be in the habitable zone and still be lifeless, like Mars. A planet outside the habitable zone might harbor life in subsurface oceans, like Europa or Enceladus in our own solar system. Understanding Mars helps us understand what makes a planet habitable, which guides our search for life elsewhere. Every data point, every measurement, every sample analyzed adds to our knowledge, refining our models, improving our ability to predict which worlds are worth studying in detail. The future of Mars is unwritten, but the possibilities are boundless. In one future, Mars remains as it is, a pristine world studied by robots and occasional human visitors, but largely left untouched. In another future, Mars is transformed, its atmosphere thickened, its temperature raised, water flowing once again on the surface, a second Earth. In yet another future, Mars is home to millions of people, cities under domes or underground, a thriving civilization independent of Earth. Which future comes to pass depends on choices we have not yet made, questions we have not yet answered. Do we find life on Mars? Does it exist today, or did it exist in the past? Or has Mars always been sterile? The answer will shape our approach. If we find life, even microbial life, the ethical imperative to preserve it will be strong. If we find no life and determine through exhaustive searching that Mars is indeed lifeless, the argument for terraforming becomes stronger. Terraforming Mars is theoretically possible. The planet has carbon dioxide locked in the polar caps and absorbed in the regolith. Releasing this CO2 into the atmosphere would thicken it, strengthen the greenhouse effect, warm the surface. Water ice would melt, adding water vapor, another greenhouse gas, creating a positive feedback loop. The process could be initiated by factories producing perfluorocarbons, extremely potent greenhouse gases, or by orbiting mirrors reflecting sunlight onto the polar caps, or by impacting asteroids to deliver heat and volatiles. Once started, the process might be self-sustaining, though it would take centuries or millennia to complete. The end result would be a Mars with a thicker atmosphere, perhaps a few hundred millibars, enough for liquid water to exist on the surface, though still too thin and too high in carbon dioxide for humans to breathe without assistance. Further steps, introducing photosynthetic organisms genetically engineered to survive Martian conditions, could begin converting carbon dioxide to oxygen. After thousands or tens of thousands of years, the atmosphere might become breathable. This is a long-term project, multi-generational, the longest and most ambitious engineering effort humanity has ever contemplated. It raises questions of responsibility, ethics, and our right to alter another world. These questions do not have easy answers, and they should not be decided hastily. There is a concept in astronomy called the cosmic perspective, the recognition that we are a small part of a vast and ancient universe, that our planet is a pale blue dot in the immensity of space, that everything we have ever known, everyone who has ever lived, has done so on this tiny world. This perspective can be humbling, even frightening, but it can also be liberating, a reminder that our petty conflicts and divisions are insignificant against the backdrop of the cosmos. Mars offers a unique version of this perspective. It is a world we can see, study, even visit, yet it is profoundly alien, a place where the familiar rules of Earth do not apply. Standing on Mars, looking up at Earth in the sky, you would feel the distance, the separation, the realization that you are standing on another planet, that the ground beneath your feet has never known the touch of rain, the growth of grass, the footsteps of animals. That realization changes you. Astronauts who have gone to the moon report a similar shift in perspective, a sense of the fragility and preciousness of Earth, the thin blue line of atmosphere that makes life possible, the interconnectedness of everything on our world. Going to Mars would amplify that feeling because Mars is not just a satellite like the moon. It is a planet, a world in its own right, with its own history, its own character, its own claim to existence. The people who go to Mars, who live there, who make it their home, will develop a new identity, a Martian identity, distinct from their earthly origins. Over generations, cultural differences will emerge, shaped by the Martian environment, the isolation, the challenges. Perhaps one day, centuries from now, Martians and Earthlings will view each other as foreigners, as people from different worlds, because that is literally what they will be. This is speculative, far into the future, but it is worth considering. The colonization of Mars is not just a technical challenge or a scientific endeavor. It is the beginning of a divergence in human evolution, biological and cultural, that will ripple forward through time in ways we cannot predict. Let the quiet settle now. The story of Mars, vast and layered, begins to fold inward like a blanket drawn close. We have traveled across billions of years, from a molten world to a frozen desert, from hypothetical seas to dust storms, from the first telescopic observations to rovers drilling into ancient lakebeds. We have imagined futures, contemplated ethics, felt the loneliness of the Martian surface and the awe of standing under its sky. Mars is a dying world, yes. Its atmosphere is thin, its water locked away, its magnetic field long gone. But it is not dead. It endures, patient and quiet, a testament to the forces that shape planets, the fragility of habitability, the preciousness of life. It waits in the darkness, reflecting the pale light of a distant sun, rotating once every 24 hours and 37 minutes, marking time as it has for eons. And we, tiny creatures on a neighboring world, look up at that red point of light in our night sky and feel called to it. We send robots first, then prepare to send ourselves. We ask questions, seek answers, dream of what might be possible. This is humanity's gift and curse, the need to explore, to understand, to reach beyond what is known into what is not. As the night wraps softly around you, as your breathing slows and sleep approaches, let yourself drift in the knowledge that Mars is out there, real and waiting, a world we are just beginning to understand. Let the vastness of the cosmos, the depth of time, the beauty of discovery settle over you like a gentle weight. Let the questions linger without demanding answers. Let the wonder remain. Mars will still be there tomorrow and the next day, and for billions of days after that. The story continues, chapter after chapter, written in dust and stone, in the data streaming back from rovers, in the footsteps that may one day mark its surface. The echoes from that dying world have not finished speaking. They whisper still, carried across the void, reaching us here in the dark, reminding us of what was, what is, and what might yet be. Rest now. Let the stars turn overhead, unseen but present. Let Mars follow its orbit, patient and enduring. Let the universe continue its vast and ancient dance. You are part of it, connected to it, made of the same stardust that makes planets and stars, atoms forged in the hearts of dying suns, now gathered into the form that is you, aware and wondering. The story of Mars is also your story, our story, the story of a species that looks up and asks why, that builds machines to carry our curiosity across the solar system, that dreams of walking on red sands under a butterscotch sky. It is a story still being written, still unfolding, still full of possibility. And in this moment, in the quiet between breaths, you are part of that story, listening, imagining, reaching across the darkness toward a world that was once alive and might, in some distant future, be alive again. Not with the life it knew billions of years ago, but with new life brought from Earth, seeds planted in Martian soil, footprints pressed into Martian dust, voices carried on the thin Martian wind. The echoes continue, the story continues, and you, here now, rest and dream, are part of the continuing. Sleep well, knowing that Mars endures, that the cosmos turns, that the quest for understanding never truly ends, only pauses, gathering strength for the next chapter, the next discovery, the next step into the vast and beautiful unknown.